The large matrix that we're going to see like would be involved, right? 2D trust interval.
They're all reasonable.
Are we looking at more than like 4 nodes?
For one of them, yes, but that's the 1D problem. So the 1D problem will have more than 4, but the 2D, but for the beam and for the 2D truss problem, I know for sure there's only 4 nodes. Yeah, that's all I'll say about that.
Sorry about that.
Hey, Aaron, how's it going? Yeah, campus was good today. Yeah, parking's still a struggle, but I think it will just continue to be for a while. It gets worse every year. Parking. They added the structure, but then they got rid of a big parking lot, and so like there's a net gain of 0, and it feels like there's more people on campus now than ever. So 1 step forward. I won't say 2 steps back, but it's 1 step forward and 1 step back. We're back to the same problem as before. All right, it's 7 o'clock, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing today? On the eve of the midterm exam, so it's the yeah, it's the stressed. I know people are feeling stressed and all this stuff. So announcement first. So I know homework 2 is due tonight, and so just so that you guys can have the solutions for homework 2 while you're studying. I'm going to post the solutions tonight, and so that'll be the last thing I do before I go to bed. So you'll have those available to you, so that you can study. Okay, and so you can look forward to those basically right after it's due time. Okay? And so our midterm is this Wednesday, and so it's going to be in-class midterm. So so please make sure you're on campus and you're here in the classroom. We were just talking about kind of parking problems before the class, but thankfully, at night. Most people go home at this point, and so parking will probably be easier at this time. So at least that'll be good. Okay, and so the midterm will take place in class. It'll be all hand calculations, and so you don't need any Matlab or anything like that. But I do recommend that you bring a calculator, just to kind of help with some of the arithmetic. Okay, because even though I think this material. I think at this point, everyone's kind of used to, writing stiffness matrices and all that stuff. Hopefully it's becoming a kind of like second nature and muscle memory. But it is going to be a challenge to kind of write everything in time. And so you want to make sure you're really efficient with your time as much as possible on the exam, because, writing those matrices is not hard. It's just time consuming. So you want to make sure that you kind of set yourself up for success in the best way possible. Okay. Okay, so any questions on the exam or the homeworks or any of that before we get started for today? Okay, all right, and so today, because the midterm's Wednesday, I thought we'd have kind of like a software day. So my original plan for today was just to do an Ansys activity, but we didn't quite finish where we on Wednesday, and so I want to make sure that we finish talking about the Matlab implementation. You know, because we were kind of stuck on kind of a crucial part, which is the assembly. And so I want to finish that up first thing today, and then we'll start the Ansys activity. And so I'm hoping to finish the Ansys activity today as well, because it's not that difficult of an activity. And so if we can, you know, let's try to do both things today. But you know, but if we don't finish, it's no big deal too. Okay, and so where we left off last Wednesday was we were learning how to implement the stiffness method in Matlab. Okay, and in particular, we were doing it for a frame problem. Okay, and so frames are a great, I think, candidate for Matlab code because it's just so tedious to do these problems and you know, by hand. And so we can make a code that automates most of this for us. You know, that saves us a ton of work. Okay. And I think this is a great example too, because I think it illustrates a lot about how finite element codes are structured in general. You know, even though you know these problems are, you know, probably a little bit too simple to solve in Ansys, you know, just going through the implementation and how we set up the variables and stuff like that for these kinds of problems, I think gives you a really good idea for, you know, how these are actually implemented in practice. And for the final project, you know, we're going to take a very similar structure to the code, although our final project will be quite a bit different than this. Okay. Okay, and so last time we talked a lot about the data structures. We talked a lot about, you know, the variables that we set up. We talked a lot about things like the connectivity matrix. Okay, we talked a lot about the material properties. Okay, we also talked, I think we spent the most time talking about how to compute the element stiffness matrices. Okay, and so if you still have your code from last week, then that's great. We're going to pick up right where we left off. But basically, what we did last week was we computed the element stiffness matrix for a you know, for a frame, you know, using Matlab. Okay, so this kind of 6x6 monstrosity, you know, that's normally very difficult to compute by hand. You know, we wrote Matlab code to solve this for every single element in our mesh. Okay, and so the place where we left off was here. Okay, and so now that we've computed all the element stiffness matrices, the next step is to assemble that into the global system. Okay. And so you've all done this by hand probably dozens of times at this point, right? And you know, I think this is the part that I think is, you know, from the programming perspective, I think this is probably the most difficult to understand. Okay, and so let's kind of break this up kind of step by step. Okay. And I think, you know, I think when you have code like this that's in a loop like this, I think it's really easy to kind of get lost and kind of, you know, what's going on in every iteration of the loop. And so for these kinds of programs, what I think is best is to just focus on just one case, right? So just focus on one case of the loop, one iteration of the loop, and then kind of work your way through the logic of all of that, and then, you know, and then the rest will come, you know, the rest will kind of follow that same logic. Okay, and so for this particular problem, let me go back to the slides. Okay. Let's focus on just the element stiffness matrix for the first element right here. Okay, and so you can see here we have an element, its nodes are 1 and 2. Okay, and so if we wrote the element stiffness matrix for this, it would have 6 degrees of freedom. So it'd be U1x, it'd be U1y, theta 1, U2x, U2y, and theta 2. And so this is really convenient because, you know, we know where this should go in the global system, right? And so in any global system, because it's, you know, it's because it's node 1 and 2, right? And so here's, you know, let's say, well, that was a lot more than I thought. Okay, and so let's say here is our global matrix, right? Since we know that element 1 here acts on nodes 1 and 2, we know that's going to occupy, you know, the top left quadrant, right? Where this is like U1x, U1y, ... and this ends with theta 2, right? And so we know that for this element, you know, it's going to be inserted into this socket right here. Okay, and so let's go through the code kind of line by line to kind of make sure that we take the element stiffness matrix for this, you know, for this element and insert it into the right place. Okay. Okay, so let's go back to the code here. Okay. All right, so let's kind of take this loop and let's kind of break it down kind of line by line. Okay. Okay, so we enter the loop. Okay, and so, you know, for all of this, even though we're inside the loop, let's assume we are working on element 1. Okay, and so all of these things that we're computing, you know, they're going to be for element 1. Okay. Okay. And so first thing, first thing we need to do is we need to find out, or we need to poll what nodes are connected to this element. Okay. Because at this point we don't know. Okay. And so normally, the way we do this by hand is we just look at the picture, we just look at the image, right? And we look at which nodes are connected here. Okay. But in Matlab, we don't have the picture that's programmed in Matlab. What we have instead are variables which store our data. Okay. And so the data structure that we use to store, which nodes are connected to which element, remember, was our connectivity matrix. Okay. And in fact, we have two of them, right? And so we have, N1 and N2. Okay. And so N1 is a number which states the first nodal ID for this element. Okay. All right. And so let's look at our diagram here. So what's the first node that element 1 is connected to? We should call this element A, I guess. Okay. Right. It's node 1, right? And so that means when we write our program, right? When we write our program, this N1 should have a value of 1. Okay. And then N2 is going to be the second node that's connected to this first element. And so N2 is going to have a number of 2 attached to it. Okay. So N1 is 1, N2 is 2. Okay. So very, very simple for this. Okay. Next. All right. So I think this is the part that I think is generally kind of confusing. And so what we need to do here is we need to compute where in the global matrix that we need to start inserting values, okay? Because eventually, just like I mentioned here, right? Eventually, after we computed the 6x6 element stiffness matrix for this first element, we need to stick it into the global system somewhere, okay? And if you think back, actually, let me bring up this slide right here, okay? Even if you didn't think about it before, the way that you kind of construct these 2D problems, and 2D trusses have the same thing, is that you take each quadrant of the element stiffness matrix, and these quadrants always stick together in the global system. Okay. And so when we insert this into the global system, these pack of 9 elements here these pack of 9 entries always stick together. These pack of 9 entries always stick together. Same thing with these 9 and these 9. Okay. If you think back to when we did our 2D truss problems, right? Our 2D truss problems were, our element stiffness matrices were 4x4, right? Okay. You can do the same thing, and you can look back at all of our past examples and to kind of confirm this, right? And if you break up that 4x4 matrix into 4 quadrants of 2x2, right? Okay. What you should notice from the, from when you did assembly, no matter what the nodes are. So let's say that this is node, our particular 2D truss element was connected to nodes 1 and connected to node 6, right? And so 2 numbers that are pretty far apart. Okay. What you'll notice is that when you did the assembly, when you inserted this into the matrix, the global system, you always had a 2x2 pack that always kind of stuck together. Okay, because this is the node 1 pack. And so this node one pack always stuck together, okay? This pack always stuck together because this was everything for node 1 in terms of the rows and node 2s on the columns, okay? These 4 always stuck together because they were, node 1 on the columns and node 2 on the rows. And then this pack of 4 always stuck together as well. And so that's because this is the node 2 pack and the node 2 pack. Okay. If you go back to all of our examples, you'll see that this is always true, okay? And so for frames, we're doing them in arbitrary directions, right? And so we're going to have the same kind of packs here, right? So this is kind of like the node 1 pack right here. This is the node 1, node 2 pack. Node 1 on the rows, node 2 on the columns. This right here is node 1 column, node 2 row pack. Okay. And this last one is node 2 rows, node 2 column packs. Okay. And so we're going to leverage that pattern to assemble them together. Okay? And so we're going to assemble each of these kind of packs together into our global system. Okay. Okay. So that kind of makes sense. So does everyone kind of see that pattern in how we assembled the element stiffness matrices? Okay. Okay. So let's use that logic in assembling this. Okay. And so what I'm doing here is I'm basically computing the starting indices for each pack. Okay. And so IND1 is the starting location in the global matrix where we're going to start inserting, that pack, right? And IND2 is going to be the location for both the row and the column index where we're going to start inserting the pack for node 2, okay? And so to compute this, we're going to have the same formulas up there. Okay, so we're going to have 1 plus 3 times n2 minus 1, okay? And this is going to give us the correct starting location. Okay? And so the key quantity to know here is the 3. Okay. The reason we have a 3 here is that for frames, we have 3 degrees of freedom per node. Because for frames, we compute the x displacement, we compute the y displacement, and we compute the rotations as well. Okay. So every time we basically move from one node to another, right? And so if we go to the global system, I don't have an example of that here, okay? But we can still see it in this element system, right? And so if we go from node 1 and we say to node 2, right? We have to skip over 3 values, right? Because we have to skip over 1x, 1y, and theta 1, and then finally we reach the first thing for node 2, okay? If this were to continue, so let's say this is the global system and we have, U3X, U3Y, right? In order to get to the starting location for node 3, we have to skip over 6, right? And so we have to skip over all the node 1 stuff, which is 3 of them, all the node 2 stuff, where there's 3 of them, and then we finally get to the node 3 stuff, okay? And so that's why we have 3 here, okay? And so that's 3 just to indicate that there's 3 degrees of freedom per node, okay? We have a 1 here just because, we start counting at 1. We don't start counting at 0. Okay. And so that's all the 1 does. And then next we have the nodal ID, right? Remember the N1, N2 here is a nodal ID. Okay. We have nodal ID minus 1. Okay. Just to make sure that we start at 1. Okay. And so when N1 is equal to 1, you can see here that we start, our IND1 here is at 1. Okay. Because since node 1 is connected to element 1, okay, that means we're going to start inserting at the first row and the first column of the global system. Okay, and so that's what IND1 represents. And IND2, IND2 is referring to node 2, and so N2 is 2 for element 1. And so if we plug 2 in here, you can see that we get 4. And so IND1 is going to be 1 and IND2 is going to be 4. Okay. And so kind of remember that as we start assembling this matrix. Okay. Any questions on any of the logic behind this so far? Okay, and so now that we kind of understand what IND1, IND2 are, what's important about these is to remember IND1 and IND2 are locations in the global system. Okay. Because we have two kind of matrix systems that we're juggling right now. We have the element stiffness matrix, and we want to insert that into the global system. Okay. And so IND1, IND2, these are the locations of the global system. So kind of remember that as we're going through this. Okay. Okay. And so this next line of code, this is just a little bit of bookkeeping, and so this is this is not too important. But just to kind of make things a little bit simpler, what I'm doing is I'm basically extracting the element stiffness matrix for this particular element. Okay. Because normally if you want to do this line is optional. And so another way you can do this is you can replace this with K, LM, at 1, 1, IEL. Okay. But I thought that's kind of a hassle to keep writing that. So what I did was I just basically extracted this element stiffness matrix. Okay. Okay, and so that's basically what the tooltip says. Okay, and so we're basically retrieving the current element stiffness matrix that we're interested in inserting. Okay? But this, is not too important. So this is something that you can just copy. Okay. Okay. And so the next part, this is where things I think get a little bit tricky, because this is when we actually start inserting things into the global system. Okay. And I'm going to do this pack by pack. Okay. And so what I'm going to start with is the top left 3x3 part. Okay. And so this is going to be this pack right here. Okay. And so this is going to be the pack for node 1 column and node 1 row. Okay. All right. And so let's go ahead and logic this out. Okay. And so for this element stiffness matrix, right? For this entry right here, okay. This entry is the 1, 1 entry of the element stiffness matrix, right? This should be inserted, because this is referring to node 1, this should be inserted into the global matrix in the 1, 1 slot. Okay. Global. Spelling is hard. Okay. And so let's look at our code just to see if we're doing that exact thing. Okay. Okay. And so let's look at this first line here. Okay. All right. There's a lot going on in this line, so let's kind of break it up, kind of step by step. Right. Okay. So the first thing we have is K glob at IND1, IND1. Okay. What is IND1 for this loop? Right. So IND1, remember, is 1. Okay. And so this is the location in the global matrix. Okay. And so we come back down here, we can say that, what we're specifying here is the value for the 1, 1 slot in the global matrix. Okay. This next part of the statement here is equal to K glob at IND1, IND1. All this is saying is that we don't want to erase what's there already, right? And so if you think back to our Matlab review, remember we had our update notation, right? And so when we wanted to, when we wanted to add to an entry in a matrix, but we didn't want to overwrite its value, we have to use kind of the same thing on both sides of the equal sign. Okay. And so the fact that this is here, the second one is just to make sure that we don't overwrite what's there already. Okay. Okay, and then to that, we're going to add the element stiffness matrix entry at 1, 1. Okay. All right, and so if you read this kind of whole line together, what we're saying is that the 1, 1 entry of the global matrix is equal to the 1, 1 entry at the global matrix, which is what was there already, plus the 1, 1 entry in the element stiffness matrix. Okay. And so we're taking basically the very top left entry of the element stiffness matrix and then adding it to the appropriate spot in the global matrix. Okay. Okay. So does that make sense? Any questions on how we did that? This one's a little bit, I kind of wish I chose element 2 because this is, because we're going to end up kind of matching up, the same indices for the global as the as the element, but I think that's okay. Okay. All right. So that's element 1. I mean, that's entry 1 for element 1. Okay. Next, we're going to go across the row. Okay. And so the next thing that we're going to add is this entry right here. Okay. And so this is in the 1, 2 slot. Okay. Row 1, column 2. Right. And if we think about this just by hand calculations, right, we know that this entry right here is going to go into the 1, 2 slot of the global matrix as well. Okay. And so let's make sure that our code does that. And so if we have on the left right here, we have IND1, which is 1. And then we have IND1 plus 1, which is 2. Okay. And so we have 1, 2. So that's good. Okay. And then for the element stiffness matrix, we're adding in the 1, 2 slot as well. Okay. And so what we're saying is that the 1, 2 slot of the global matrix is going to be equal to itself plus the 1, 2 slot of the element stiffness matrix as well. Okay. Okay. And so we basically, go away Excel. And so we basically added the second entry of the element stiffness matrix into the global one. Okay. And so we're going to do this for element per element. Okay. Or excuse me, entry per entry. Okay. So next we're going to do the 1, 3. Then we're going to do the 2, 1, and then 2, 2, then 2, 3, then 3, 1, 3, 2, and 3, 3. Okay. And you can see here that the code kind of proceeds in that exact logic. Okay. And so in total, per pack, right? So each pack is 3 by 3. And so you should have 9 lines of code here that correspond to it. Okay. I think the big thing to remember when you're writing this code is that when you're referring to the global matrix, okay. And so whenever you're referencing an entry in the global matrix, you have to use IND1 and IND2, okay, right? Because otherwise you're going to end up in a different spot. But for the element stiffness matrix, since the element stiffness matrix is a fixed size, since we basically always know the element stiffness matrix is going to be 6 by 6, then we can put in the indices for this using hard code. Okay, so we can just call the 1, 1 entry for that. Okay, and so just to kind of repeat, for the global element stiffness matrix, we have to use IND1, IND2, but for the element stiffness matrix, we can just use hard coding 1s and 2s and 3s and so on and so forth. Okay. Okay, and so I've implemented this first pack for you, and so all this should be correct. Okay. Next, we're going to do the next pack. Okay, and this is where IND2 comes into play, right? So let me kind of write this over here. Okay, so remember, IND1 is equal to 1, IND2 is equal to 4. And so now we're going to work on the second pack. And so the second pack is the top right, okay? And so that's going to be this pack right here, okay? And so we're going to start at 1, 3, and then we're going to 1, 4, 1, 5, 1, 6, okay? And so let's make sure that our code does that as well, okay? All right, so let's start with 1, 4. And so we can see here that we have 1, 4 for KE, okay? And then for K glob, we're doing IND1 and IND2, okay? And so if we look at what IND1, IND2 are, we see IND1 is 1, IND2 is 4, right? So we have 1, 4, okay? And so that makes sense, right? And so that's why we're adding the 1, 4 entry for that. And we do the same for 5 and for 6. Okay. And we use +1s and +2s for the INDs, because they're that's how we get the different entries in the global matrix. Okay. Okay, so just to make sure that we get to the Ansys activity, I'm gonna go ahead and fill this in for you. Okay, and don't worry. So after this, I think the full code is posted online as well. And so I think if you go to our files, let me check. When you go to code, yeah. Oh, actually, I haven't uploaded it yet. So after class A, I'll upload the full solution so you can kind of see it. But let me go ahead and type some of these in for you. Okay? But I want to make sure we get to do some Ansys today. Should be that. Notice how everything in this block, the first entry here starts with IND1, and the second entry is always IND2, right? And if you look at this next block, it's swapped. And so since we're doing the bottom left entry of the element stiffness matrix, we do IND2 first, and then IND1. And then for the bottom right, we do IND2, IND2, okay? And so I try to do my best to kind of structure this code as logically as possible, but I think there's still going to be a lot of questions, because this is a fairly complex code. There's no other way to kind of get around that. And so I don't expect everyone to pick up this code or to kind of understand everything right away, because there is a lot going on. But what I hope is that this will be kind of a good reference for you, and as well as these lectures, and as well as the slides. And as you kind of go through it and you kind of talk yourself through it, then some of the logic and some of the structure kind of makes a bit more sense. Okay. I'm just going to fill out this section, and then I'm going to go on to the boundary conditions. This code's not going to run because this is everything above this is incomplete. Okay, and so that's the second pack, I think. Okay, and so we covered everything from 1,4 to 1,6 all the way down to 3,6. Okay, and so that covers everything in there. Okay. All right, any questions on this? 174. Thank you. Yes, I didn't miss that. Okay. All right, any questions on this? Okay. Yeah. So you know the bottom left pack and the bottom right pack, you know, they follow the same logic. Okay. And so you know compare kind of what you have in your notes today along with the final solution, and then you know hopefully that logic starts to make sense. Okay. And then you know as you go through this code, you know try doing this try doing this loop in your head or on paper for the second and third elements as well. Okay. Because I think those will be a little bit more talented. Okay. And so, you know, to kind of help you understand the code, you know, again, you know, the best way I think to understand code is to go through it kind of manually and just apply it to an example and just make sure that you get the result that you expect. Okay. Okay. All right. So that's assembly. Okay. So I think assembly is kind of the most difficult part. Okay. So next we're going to apply the boundary conditions. Okay? And we're going to do this in 2 steps. And so the first step we're going to do is the Dirichlet boundary conditions. Okay. And so remember, these are our fixed supports. And so our fixed supports, remember what we do for this is that we replace an entire row of the matrix. Okay. And so after we've done all the assembly, if we have a fixed support on a certain node, that means we're going to replace that row. Okay. And so we're going to put a 1 on the diagonal and 0s everywhere else. Okay. And so let's see how that's implemented in code. Okay. All right, and so we have just four lines in this loop. Okay, and in fact, I've already kind of written 2 of them for you. Okay. Okay, and so if we go to this loop right here, okay, what we're doing here is I'm looping over all the Dirichlet boundary conditions. Okay, and so if you remember from last time, you know, at the very beginning of the code, we defined this vector right here for Dirichlet BC index. Okay. And what these were, if you remember, these were all the row numbers where we want to apply Dirichlet. And so for this particular problem, you know, we had fixed supports on nodes 1 and 4, right? And so that means we're going to apply a Dirichlet boundary condition on U1x, U1y, and theta 1, okay, as well as U4x, U4y, and theta 4, okay. All right. And so when we went to actually apply this into our, you know, let's say that we did this by hand, you know, what we would do is we would take, you know, the rows that were associated with these degrees of freedom, and we would zero them out. Okay. And for U1x through theta 1, we know this is going to occur in rows 1, 2, and 3, right? Because those are the first nodes, and so those will be the first 3 rows. And then for U4x, U4y, and theta 4, this is going to be rows 10, 11, and 12. Okay. Right. And so if you if you remember from last time, what we said was that this Dirichlet index, you know, that means we want to apply these Dirichlet boundary conditions on node 1, 2, 3, okay, and then 10, 11, 12. Okay. right? And so once we've specified that here, what we're doing this in this loop right here is basically looping over all those entries. Okay. Okay, and so again, for this one, whenever you have a loop, just apply the logic to just one entry in the loop, and then the logic will kind of and then you're going to apply that same logic to all the other loops. Okay. And so let's do this for the first entry. Okay. And so for the first entry of the loop, what we're saying is that we're going to zero out the first row. Okay. Right. And so we're going to take the first row because that's associated with U1X, and we're going to completely zero it out, okay, to apply this boundary condition. Okay. Okay, so the first thing we're going to do is we're going to extract. Okay, so this is going to retrieve the index for the Dirichlet boundary condition. Okay, and so for the first entry, we have this IND dir. Okay. Okay, and so this is going to be 1 for the first iteration, okay, because that's going to indicate the first row of our matrix. Okay. Okay. And so the next thing is we're going to zero out this entire row. Okay, and so we're basically going to say that k glob at this row, for all the entries in this row, this is going to be zeros. Okay, and so I'm going to go ahead and fill this in just because this is you might not know that you can do this. Okay, but when you have a excuse me, you want to zero out an entire row of the matrix, you can actually do it in one line of code. Okay. And so what you could say is that this entire row is going to be equal to zeros, 1. Okay? So this is going to be a vector that has 1 row, and the number of columns that we're going to have is n nodes multiplied by 3. Okay. Remember, because we have this variable here which stores the number of nodes, and so let's take n nodes, and we're going to multiply it by 3. Right, and so what this is going to do is that this is going to create a vector with 1 row, and in this case 12 columns. Okay, and it's going to set this entire row equal to that. Okay, and so that's an effective way to zero out the entire row. Okay. All right, so the other thing we're going to do is we're going to set the diagonal entry equal to 1. Okay, and so the diagonal entry for the first iteration is going to be 1, 1. Okay. Okay, and so one way to access the 1, 1 entry is to use IND-dir. Okay, so we do IND-dir, IND-dir. Okay, and this is going to be equal to 1. All right, and so after these 2 lines of code, what's going to happen is that in our global matrix, the first row will be all zeros except the diagonal entry, which will be right. And so that's essentially what these 2 lines of code are going to do. Okay, so these 2 lines of codes, first of all, we're going to zero out this entire row using the special zeros command in Matlab, and then next we're going to set the diagonal entry equal to 1. Okay. Any questions on that? Okay. Okay. And then the last thing we're going to do is we need to set the forcing vector equal to 0 on that row. And so what we say is f glob at the at this index is going to be equal to 0. And so that's already all done for you. Okay. Okay. All right. And so next we're going to do the same thing for the Neumann boundary condition. Okay. And so here I've written most of the code for you. And so this follows almost the exact same logic as our Dirichlet boundary condition, except there's less to do, right? Because remember, when we apply our loads, we apply this force right here or this moment, we don't modify the matrix at all. We just take these values and just plop them into the forcing vector, right? And so we plop them into the right-hand side vector, right? And so that's exactly what I'm doing here. And so first what I'm doing is I'm extracting the row, okay? And so whenever you see index here, that means basically row in the system. Okay. And so in other words, this is the row in the matrix where we're going to apply this condition. Okay. And so that's going to be listed by a separate vector. Okay. And so remember, we also constructed this vector last time, which was the row, which lists the rows in our global system where we have to apply our mode type boundary conditions. Okay. Okay. And so next thing we're going to do is we're going to retrieve the actual load value. Okay. And so if you remember from last time, we also have this vector right here, or this variable, noi BC value. Okay. And this is where we actually store the BC values. Okay. Right. And so for this particular problem, we have one entry with a positive 10,000 and another entry with a positive 5,000. Okay. One to indicate an X load, another to indicate a moment here on node 3. Okay. Right. And the last thing we're going to do is we need to apply this to the left-hand side, to the right-hand side. Okay. And so this is going to be IND and NEU. Okay. Right. And so that tells us we need to assign this boundary condition on this row of the matrix. Okay. And then the value that we're going to specify there is the actual load value that we just extracted. Okay. And so this entry right here should be the same as this entry. Okay. Okay. But the logic between the two boundary condition loops is very similar. And so you're going to loop over, you're basically going to loop over all the boundary conditions. You're going to extract the row in the matrix that you need to act on. You're going to extract, if relevant, you're going to extract the value, and then you're going to apply those changes to the left-hand side matrix and the right-hand side vector. Okay. Okay. Any questions on this? All right, and so from there we're basically done. And so the last thing we need to do is we need to solve. Okay, and so this is the part of a hand calculation where you normally normally ask Matlab to solve it for you. Okay, and so but the only difference now is that the global stiffness matrix and the right hand side forcing vector are already done for you. Okay, and so the only thing you need to do here is you need to say K glob, which is our global stiffness matrix. And you're going to backslash F glob. Okay. And so once you do that, and you can run this code, and unfortunately I can't run this because I didn't think to save the code that we wrote last week. Okay, but after you run this code and you come back to the console, you should see an additional variable here called useSol. Okay, and that useSol will have your finite element solution. Okay. And in fact, one thing you can do is you can take the semicolon out, and then it'll print the solution directly to the console, and then you can just read the solution off there. Okay. All right. And so that's the MATLAB implementation in a nutshell. And so again, this is a complex code. This is not an easy code to kind of tackle, right? And so in some ways, it kind of feels disingenuous to me because we did kind of MATLAB activities before, and we had the homeworks, and they were cute little for loops and stuff like that. And all of a sudden, I'm dropping you into this massive code here, And so I know it's a lot, and so kind of take it kind of step by step. Look back on the lectures again, look through the slides. I try to be as detailed as I could with the slides. And as like I mentioned last time, think about how you would solve these problems normally, and think about how would you do those exact same steps as you would by hand, but how do you instruct a computer to do those same steps? Okay, and if you think with that kind of logic, then I think a lot of the structure and a lot of the organization of this code, I think, starts to make more sense. Okay, but again, I think it's one thing where you're going to have to kind of go back to the lectures, kind of go back to the slides. Talk to me about it. Of course, I'm always happy to go through the code with you, look through the solutions for this code, and kind of parse it, kind of section by section, and then hopefully that kind of starts to make things make a bit more sense. Okay. Okay. So any final questions on this before we move on to Ansys for today?
Sir, can you scroll down for the last line?
Wait a second.
Can you scroll down for the last line?
Oh yes. Yeah, I'll post the finished code. So this code's only like half finished because we started kind of halfway through, but I'll post the finished code after this just so that you can have it to refer to. Yeah. Okay, all right, and so that's it for MATLAB. And so next thing we're going to do is we're going to do our next Ansys activity. Okay, and so if you're at home and you're on your laptop, you can go ahead and open up Ansys Workbench. But if you're here in the lab, you can open up Ansys Workbench. Okay, and oh, I had it. Okay, and so you can see that the activity is already uploaded, and so it's Ansys Activity2. Okay. And for Ansys Activity2, we're going to do an Ansys simulation on a bike crank. Okay. And so I timed this, very deliberately because we're kind of in a transition right now because we're basically finished with all the direct stiffness stuff, and so all the trusses, beams, and frames, we're never going to see them again after the midterm. And so after that, we're going to start going over more general finite elements. Okay, so strong forms, weak forms. Galerkin forms, things like that. Okay, so we're kind of at a transition point, and so I timed this Ansys activity so that we kind of remember, remember why we're kind of going through all this theory, because I know it's kind of a slog, but it all kind of contributes to a code like this. Okay. Question for the homework: we only have to do 3A and not 3B. Yes, correct. Yeah, and so for the homework 2, only do 3A. 3B is still going to show up, and so 3B is going to be at the end of this activity, but you're not going to do it by hand. You're going to do it with your code. Okay. Okay. All right. So let's get started with Ansys Activity2. Okay. Okay. And so last time we saw Ansys, it was basically just kind of a get to know you kind of activity, right? And so I think for a lot of people, that was probably your first time using Ansys, and so we did just a simple 2D simulation on a plate with a hole. Okay. For this one, I want to do a little bit of a more realistic situation. Okay, and so I call this the bike crank activity because we're actually going to simulate the crank on the pedal of a bike. Okay, and so it's not a very nice bike crank. I know, it's not very realistic. Real bike cranks look much better than this. But it's simplified, just so that it can work well in Ansys. Okay. Okay. And so of course, compared to our first activity, we're working with an actual 3D geometry this time. Okay. So we're not doing 2D anymore. So we're doing 3D. And so that's going to be a big difference. Okay. And another thing that's going to be different here is that, I'm not going to explicitly tell you, where the loads and the constraints are going to be. Okay. And so a big part of using finite elements is kind of making those decisions yourself. And so you have, a lot of times you work for a company that's going to ask you to do finite elements. You're going to get a CAD file from, your design engineer. Okay. And your boss is going to say, here's our geometry, figure out if it's going to break or not. Okay. And so it's going to be up to you, the engineer, to say, where does it make the most sense to add our fixed constraints? Where does it make the most sense to add loads? How much load should I put on? Okay. And what's the worst case scenario? Okay. And so as we're going through this activity, I want you to think about, what's the worst case scenario, or what's the scenario that's most likely going to cause this bike crank to fail? Okay. And then you're going to simulate that in Ansys. Okay. Okay. All right. And so another thing that's going to be different is that, we're going to use a custom material. And so we're going to, instead of using the built-in structural steel that's in Ansys, we're going to instead use a material, aluminum 6061, which has a Yams Modulus of 1 × 10⁷ psi and a Poisson's ratio of 0.33. Okay. And so we're going to learn how to add in this custom material as well. Okay. And the other thing is, I'm going to give you the CAD file. Okay, so we're not going to be constructing the CAD file, right? And so I'm going to give you the CAD file that you can just import directly into Ansys, and then we can just launch the simulation from that. Okay, so this is more typical of your general workflow. Okay, and so even though Ansys has a CAD software itself built in, it has design modeler and it has spaceplane. They kind of suck compared to SolidWorks, and so most of the time, most people prefer to use SolidWorks to do their CAD just because it's a lot more fully featured. Everyone kind of learns how to use SolidWorks in school, and so everyone's familiar with it. And so a lot of times you're going to have CAD models that's produced in SolidWorks, and then you just import that into Ansys. Okay, and so we're going to go through that workflow today. Okay, and so if you go to the Canvas site, in addition to the activity specs, you can see here that I have a CAD file that you need. Okay, and so you're going to need to download this CAD file as well in order to do the activity today. Okay. Okay, and so with that, let's go ahead and come into Ansys. Okay. And the first thing we're going to do is we're going to create a custom material property. Okay. All right, so let's go ahead and open up Ansys. And then we're going to start by creating a static structural simulation. Okay. And so just like last time, you're going to take static structural here and you're going to drag it into the project area. Okay. And so this is going to create your static structural, analysis type. Bless you. And so the next thing we're going to do is we're going to double click on engineering data right here. Okay. And this is going to allow us to create a custom material. Okay. So let's go ahead and double click engineering data. Okay. And after double clicking that, you'll come to this menu right here. Okay. And so last time we didn't do anything with this menu because we just used the default structural steel. But now we're gonna see how to actually apply a custom material here. Okay. And for a lot of cases, this step is going to be really important because you want to make sure that your material properties match up with whatever geometry that you're trying to simulate. Okay. Okay. And so was everyone able to get to this point right here and open up Ansys and get to this engineering data? Everybody good? Okay. Okay, and so the next step is we're going to add our material. And so you can see here that from the tooltip, you can see that there's a little help line here to say, click here to add a new material. Okay. All right, so let's go ahead and do that. So let's go and click here. And the first thing it's going to ask us to do is it's asking us to provide a name for a new material. Okay. And so you can call your materials whatever you want. And so there's no limitations on it. But generally, the most useful thing for you is to name your materials based on whatever you're actually simulating. And so since we're simulating aluminum, so let's call this aluminum. Okay, 6061 T6. Okay. Great. And then you can hit enter to to finalize that that entry there. Okay. And you can see here that we've created our new material. Right. But you can see here that there's a question mark next to it. And so that question mark is telling us that we need to specify some additional properties in order for it to become a real material. Okay. And what's missing here is information on the Yams modulus. Okay. As well as the Poisson's ratio. Okay. All right, so let's go ahead. Let's go ahead and figure out how we can add those that data in here. Okay. And so that data for Yams modulus Poisson's ratio, where we're going to go is we're going to go to linear elastic. Okay. And so if you look at this toolbox on the left, these are all the different properties that you can add to your material. Okay. And so you can see here there's a lot that you can do. Okay, and so you can add hyperelastic material properties, you can add plasticity, you can add creep, you can add fatigue life, strength, viscoelastic, there's a lot that you can add it because there's a lot of different simulations that you can run. But for a basic kind of structural simulation like this, the minimum properties that you need to add is just the Yams modulus and the Poisson's ratio. Okay, and so let's go ahead and double click on this. Okay. And so we want isotropic elasticity because that's the simplest thing that we can do. Okay. And after you double click isotropic elasticity, you'll see that a new menu will show up down here where we can add in the Yams modulus and the Poisson's ratio. Okay. Okay. So was everyone able to get to this part of the, everyone able to add these two properties right here? Okay. Okay, and so let's go ahead and add in the Yams modulus. And so if we go back to the problem specs, you can see here that we have a Yams modulus of 1 × 10⁷ psi, as well as a Poisson's ratio of 0.33. Okay. Okay, so let's go ahead and add those in. All right, so let's start with the Yams modulus. And so the Yams modulus, is given to us in PSI. So let's make sure that we swap the units, okay? And so you want to input the Yams modulus in different units. You can click on this down arrow right here, okay? And let's change this to PSI because that's the units that we were given the Yams modulus in. Okay? And so let's switch this to PSI, and then let's set this to 1 times 10 to the 7th, and so we can just do 1e7. And the Poisson's ratio, we can just set it to 0.33. Okay. And then after specifying these, it'll populate the bulk modulus and the shear modulus, based on the material model that we specified. Okay, which in this case is just isotropic elasticity. Okay. Any questions on this? Yeah, Poisson's ratio is 0.33. All right, and so that's the material properties, and so we're done with that, and so let's go ahead and exit out of here. Okay, and so the next thing we're going to do is we're going to import our geometry. Okay, so remember, like I said, we're not gonna cat up the geometry, so we're not going to sketch it and extrude just like last time. Okay, we're just going to simply import it, and so to import a geometry, you're going to right click on the geometry entry right here. Okay, and then you're going to go to the line called import geometry. And then you're going to click on browse, okay? And then after you click on browse, you're gonna browse through wherever you downloaded the crank assembly.x_t, and then you're going to import that directly into into Ansys, okay? All right, so I'm going to go ahead and do that, and so I'm going to click on browse right here, and I believe my crank should be in downloads. Yes, okay. And so when you find the crank assembly, okay, you could just double click it and it'll load, or you can just click it once and then click on open. Okay, you basically are specifying this as your geometry. Okay, so I'm going to go ahead and double click this. Okay, and you'll see right away that the geometry was loaded successfully if you have this green check mark next to geometry. Okay. And kind of generally speaking, as you go about using Ansys, if you have a green check mark, that means you're usually good. Okay, so that means that Ansys has all the data that it needs from that part, and you are ready to go on to the next step. Okay. All right, and so the next step will involve launching Ansys Mechanical. Ansys Mechanical is our program where we're actually going to run, apply our mesh and boundary conditions. And so to open up Ansys Mechanical, you can double click on model right here. Did I do it? No, I didn't. There we go. Okay, and so when you double click on model, it'll open up Ansys Mechanical for you. Okay. And if you're in the lab, you might get a pop-up that says, will you allow it through the firewall? You can just hit cancel and then it'll just be fine. And so if you have Windows security alerts, don't worry. Ansys is it's only just tracking all your clicks and everything and selling it to the government, so it's nothing to worry about. Okay. I'm just kidding. They're not doing that. Okay. And so if you get another pop-up that shows up here, you can get rid of it by left clicking on geometry here on the left. Okay. Okay. So was everyone able to open up Ansys Mechanical and they see the bike crank here? Okay. Right. Everyone on Zoom doing okay? I can't see you guys nodding on Zoom, but I'm assuming you guys are okay. Great. Okay. Okay. All right. And so we have a few steps that we need to perform here before we actually start meshing. Okay. And so the first thing we're going to do is we're going to do what we call suppression of some parts. Okay. And so you can see here that just kind of judging by the name of this part, this was an assembly, right? And so we have crank_assembly, but we're actually only interested in this part right here. Okay. Okay. And so we're not really interested in this, which is kind of the pedal, and this kind of this kind of fitting piece to kind of make sure the pedal fits with the crank. Okay. And so this is a pretty common situation in finite elements. And so a lot of times you'll be given a CAD file oftentimes by a design engineer, which has some extra parts to it that you don't actually need in your analysis. Okay. And so Ansys has this nice feature where if you load in an assembly into Ansys, you could suppress some of these parts and not include it into the simulation. Okay. And so for this particular for this particular project, we're not really interested in the pedal, right? And so what we can do is you can come up to the geometry kind of subtree right here, go to the pedal geometry. We can right click it, and then you're going to go to suppress. Okay. Right. And so if you click on this, entry right here, then what you can do, you can read the tooltip. It says that it removes the selected body or bodies from the analysis. Okay. And any scoped objects will also be affected, so you don't have to worry about that. Okay. And so that's exactly what we want. And so we don't want this pedal to be part of our assignment or part of our geometry. Okay. So I'm going to go ahead and click on suppress body. Okay. And that's going to get rid of the pedal. Okay. And we can do the same thing for this part 9 assemb rev, 3/8 of an inch. Okay. And so we don't really need this little lug nut right here. And so let's go ahead and right click this and let's suppress it just like the other one. Okay. And so all that we're left here with is just the crank, which is what we're interested in. Okay. Okay. All right. And so that's part suppression. Okay. And so that's a very important skill to know in Ansys. Okay. All right. So next thing we're going to do is we need to assign a material property for the crank. Okay. And so if you remember from like 10 minutes ago, we defined this new material called aluminum 6061. Okay. And so we want to make sure that our bike crank is actually using that material in its analysis. Okay. And so if you left click on this bike crank, okay, and you go to the bottom left of the screen, okay, and you look at this entry right here for the material, okay, you can see that the material assignment for this bike crank is structural steel. And so we don't want that. And so we want to change the material for this to be aluminum 6061. And so to do that, we're going to left click on this, okay, and we're going to click on this arrow. And after you click on that arrow, a new menu will show up, which lets you select the material for this. Okay. And so you can see here we have several different materials, and so we can make it out of water, which is definitely not what we want. We have structural steel. We have air. Okay. And then we have the material that we created right here. So this is the aluminum 6061 T6, that we created, like 10 minutes ago. Okay. And so let's go ahead and click on this. And then by clicking on that, now our bike crank here is assigned with that material. Okay. And so now we're ready to perform our analysis. Okay. Okay. Any questions on this so far? Okay. All right. Okay, so the next thing is we need to do a mesh. Okay. And the meshing, I'm going to simplify this a bit from kind of past activities. Okay. And so for the mesh, let's go ahead and generate one. And so if you generate kind of a default mesh, you end up with something like this, right? So this looks okay. It's not the worst mesh in the world, but it's also not great. Okay. Because what I'm seeing here is that, if you look at the elements of this mesh, you can see here that we have basically one triangle here. So let me zoom in so you can see better. Okay. And so if we look at kind of the thinnest part of this bike crank, we have just kind of one triangle that kind of spans the entire thickness, right? And so this triangle spans, from the top and the bottom. So generally speaking, when you're doing finite element analysis, you want to avoid situations like this where you have one element that spans the entire thickness of whatever you're trying to simulate. Okay. And so we basically want to refine this mesh so that this element here, we at least have two elements through this thickness. Okay. And so to modify the size of the mesh, you're going to go to here. Okay. And so if you read the assignment document, you'll probably see that I asked you to create a method in sizing objects. You don't have to worry about that. And so one way that you can change the size is you can simply left click on mesh right here. Okay. Let me pull this up. I can't see the bottom left of the screen. Okay. And so if you click on mesh right here, okay, and you open up this this tab right here called sizing, right? You'll see here that there is a size that you can set. Okay. And you have to be careful because it's actually, hang on, it's not here. Element size, yes. Okay, sorry. So it's not under sizing, so it's under defaults. Okay? And so if you see here that there's an entry called element size, this is where we want to specify the size right here. Okay. Okay, so you can see right now it's under the default value. So let's go ahead and change this. Okay. And so let's do 0.1. Oh, it's under meters. Okay. And so let's change the units, because right now the units might be a little bit hard to work with because it's in meters. Okay. And so let's change these units to inches. Okay. Because right now, we're applying everything in meters, and that's a little bit kind of, that's a little bit inconvenient to work with kind of such a small byte crank right here. Okay. And so if you go to home up here, okay, and then you go to this this button right here for the units, okay, and so the units is in kind of the middle of the screen. Okay, if you click on this, you should be able to change the units. And so I think the most convenient units to choose for this one is inches. Okay, but you can also do centimeters. Centimeters also works well as well. Okay. But since we're going to apply the force in pounds, I think it's going to be most useful to use English units for this. Okay. So let's go ahead and click on US Customary Inches. Okay. And you can see here that we have a mesh size of, of 4 inches. Okay. All right. So that's a little bit too big, because this entire bike crank might be about like 6 or 7 inches long. Okay. And so let's try a mesh size of about let's try 1 inch first. Okay. All right, so let's go ahead and remesh. Okay. And you can see 1 inch actually made it worse. And so this mesh looks even worse than it was before. Okay, so let's reduce this even more. Okay, so let's do 0.5 inches. Let's go ahead and generate this. Okay. So it was a little better than before, but still kind of bad. And so let's go ahead and reduce it a bit more. 0.25. Okay. So here we're a lot better. And so you remember before, what I wanted was I didn't want one element all through the thickness. You can see here that we have 2 elements. And so we have one element just like this. We have one triangle, and then we have another triangle just like that. Okay. And so this is much, much better. And so I'd feel a lot better using this mesh than before, but we can improve it a bit more. Okay. And so let's drop it down to 0.1. Okay. 0.1 inches for our mesh. Okay. All right. So now we're talking. And so now we have, a much better mesh than what we had before, right? So we have multiple elements through the thickness. Okay. Not only in this direction, but in this direction as well. Okay. And so you can see here that, this was another kind of thin feature of our geometry. You could see here that we have multiple elements through this thickness as well. Okay. So we have one element like this and one element just like that. Okay. And so that's good. Okay. And so if you want, you can refine this even more, and that's going to be great. Okay. And so if you want to do, 0.05 inches, I think that's totally fine. Okay. And so you can see this is even better. And so you have even more mesh density there. Okay. But this kind of iterative process of generating your mesh, when you're first starting out, with Ansys, this is kind of a good exercise to go through. Okay. And so, choosing your mesh and making sure your mesh is adequate is a really important part of finite elements in general. Okay. And, you start to get a good sense for what's a good mesh kind of just through experience. Okay. And so, just kind of based on, on kind of a lot of the finite elements that I've run before, I can tell you that this is going to be a good mesh. Okay. Because if you think about it, the way finite elements works is that it solves for the solution at each of the nodes in this mesh. Okay. And so if you think of your mesh as kind of like the resolution on an image, right? I think we talked about that last time we did Ansys, right? If you want to have a good quality image, you know that you have to have a lot of pixels, right? So you have to jam a lot of pixels into a small area of space. So your mesh is kind of the same thing. So if you want a high quality solution, you need to have a mesh with a decent amount of density. Okay. And so you can see that, if we were to kind of load a digital image on top of this mesh, it would be a lot higher quality than, say we did one on this mesh, right? And so if I change this to 0.25, this is going to be a much more coarse, this is going to be a much more janky image than before, right? But for this activity, I would say at least have a mesh sizing of 0.1, and then you should be okay. Okay. Any questions on this mesh? Okay. Okay. Oh, one more thing. And so the other thing we have to set here is the element order. Okay. And so we haven't really talked about element order yet. It'll make a lot more sense once we start talking about general finite elements. So I don't want to spoil too much about it or really kind of get into it right now. But just know that for anything structural, if you're running static structural or dynamics, or excuse me, sorry, just for static structural, you want to use a quadratic element order. Okay, so you want to make sure that your element order is quadratic, and it might ask you to regenerate a mesh after that. Okay, we'll go over element order a lot more carefully later on in the class, but just for now, you can just set it to be quadratic. Okay, so that's everything with the mesh. Okay, now we get onto the boundary conditions. Okay? And so this is where this is where I'm going to let you kind of decide things. Okay. And so remember, before we run any kind of finite element simulation, first of all, we need a mesh, right? So we have our mesh here. And the next thing that we need is we need at least one constraint. We need one support here, okay? And we need at least one load, okay? And so here's a situation that I want you to simulate, okay? And so I'm not going to tell you where to, I'll give you some hints, but I'm not going to tell you where to apply the fixed support or the load, but this is the situation that I want you to simulate, okay? And so the amount of load that I want you to apply is going to be 100 pounds, okay? And so somewhere on this model, you need to apply 100 pounds. And what this 100 pounds is simulating is a person, a typical size human, pressing down on the pedal of the bike crank. Okay? Okay. And so think about the situation, right? Think about where our pedal was. And so remember back when we suppressed our geometry, we suppressed a part where the pedal was, right? And so if we were to apply this 100 pounds to simulate the effect of someone pressing down, where should we apply that force, right? And so you need to think about where you're supplying that force and also which direction, okay? But the direction is going to come into a bit, okay? Next, you need to supply a fixed support somewhere. Anytime you run a static structure, you need at least one fixed support, okay? And the location where I want you to apply the fixed support is where this bike crank attaches to the bike frame, okay? And so think about, where this bike crank attaches to the frame and then apply your fixed support there, okay? And so the specific situation that I want you to simulate is a worst case scenario, okay? And so what I want you to simulate is, given that the weight is going to be 100 pounds, okay? What's the worst possible case that's going to cause this bike crank to fail, okay? Eventually, yes. Eventually, you will ramp the load, but let's start with just 100 pounds and see, where that's going to be. And so we are almost out of time, and so we'll talk about failure and stuff next time, okay? But part of this worst case scenario. Part of this worst case scenario that I think will help you out in deciding, what direction to apply the force is thinking about, is kind of under the assumption that your bike chain, okay, the bike chain that causes, that you pedal with, that's going to lock up. Okay. And so when the bike chain locks up, this bike crank is going to be essentially a rigid, it's not going to have any give. Okay. And so if you push down on it, right? So you push down the pedal, it's going to be just completely locked. Okay. And so in a situation when this bike crank is completely locked, what's the configuration of the force that's going to be most likely going to cause it to fail? Okay. Oops. Okay. Right, and so those are your conditions. Those are your specifications for this, for the simulation. Okay, and so remember, what I want you to do is I want you to insert a fixed support. Okay, so the fixed support should be applied somewhere, and I also want you to specify a load. Okay, and the load is going to have a value of 100 pounds. Okay, and this might help too. Okay. Oops. Okay, so when you apply your load, you might have to change it to components. Okay. And so if you remember from our first activity, this is how we applied the load as well, right? And so if you apply the load as components, this lets you specify, the exact direction that you want it to go, okay? And so let's say, for instance, that you want to specify the load in the X direction, okay? And so what you could say is that we have 100 pounds load in the X direction, okay? And so that's going to apply the force, in this direction. Okay, and so I think that's where I want to stop today, because we are just about out of time. But next week, I want you to think about the situation, over the weekend, and after the midterm, of course. And then next week we'll kind of pick up this activity. There's not really much more to it, but I do want to talk about how do we define failure, and in terms of like the mechanical stresses. Okay. All right. So any final questions before we wrap it up for the day? Okay, all right. And so I guess, so next time I'll see all of you is on Wednesday for the midterm. And so make sure you guys are all here for that. Okay. And then we'll pick up this activity again on Monday. All right. So remember, your homework's due tonight, so make sure you turn that in. I'll get the solutions out to you guys, around the time when it's due as well. Okay. And if you have any other questions before the midterm, please shoot me an email, and I'll do my best to get back to you as soon as I can. Right. So best of luck studying. I'll see you all on Wednesday, and have a great evening. Yep. Yep.
What's their version of the pin support strategy, right?
That's a rule. That's a rule. So pin support is the triangle, and the circle is a rule.
When they do the solution now, they have no deformation in the Y direction, but it's free to rotate.
Yes. Yeah. So a roller has that property too. So you can rotate around a roller too.
Oh, okay.
Yeah. I think this one, it doesn't matter because it's a beam. So there's no deformation in this direction anywhere,
Yeah.
because the load's only in that direction. So for a beam, the roller is effectively the same thing as a beam. If they're going to prevent any deformation.
And then in a lot of the solutions, they just cut the shit in half. It's like,
Oh yeah, you can do symmetry too. And so if it's symmetrical, you only have to do half of it. And so then instead of doing 4 elements, you just do 2, and you cut the load in half as well.
yeah, to 40.
Yeah.
So then I would just have F1, F2, F2, F3.
Yep.
Yeah, but there has to be like, there's a moment here. There's got to be some type of moment here. Would it basically just be the opposite of these two?
Yeah, exactly.
Okay.
Yeah.
All right.
Yeah.
Okay. Thanks for that, Jim.
Mhm. Yeah. Yeah, so nuances are just kind of like, you can think of them as like special situations. And so like that's one situation we have to go Another one would be, the other one we talked about is if you apply the derivative boundary condition, but it's a non-zero value. So all the derivative we've agreed so far. And so what we're saying that the displacement is equal to 0. But we're going to have situations later on where we're going to have a derivative boundary condition that's non-zero. And so like when we do, after the midterm, we're going to be working mostly with the heat equation. And so for heat equation, when we apply a derivative boundary condition, it's going to be a specified temperature. And so we're going to say the temperature at this boundary is going to be 50. And so we're going to apply the same methodology of traditionally, but instead of putting 0 on the right hand side, we put 50. So those are the two nuances. Yeah. Yeah. Okay, let me make sure I get this before you use the Zoom call. All right, sorry. I have you. Let's see. Yes, yes. So for the midterm, you should know some conceptual stuff due to about frames, but I'm not going to ask you to do any problems regarding that. Yeah. So all the problem solving problems will be either trusses, springs, or beams. Yeah, but you can expect at least one conceptual question on frames. Yeah.
They don't have a lot of trust on roller questions in here, but they have this, but the only problem is this roller is not.
Yeah, we didn't cover that. It's complicated. So you have to kind of break this, but it's not. Exactly. Yeah. So yeah, so you kind of have to break the roller into like, you have to do a transformation matrix for the roller, and then that makes it weird for your machine. Yeah, I skipped that on purpose because it's kind of too much. And the whole reason I do this direct stiffness unit is to just kind of introduce you to that process. That's kind of getting too much into the details. Like if you want to actually do structural analysis, trusses and frames, which is fine. But I think it kind of takes away from what I want to do. So I skipped it on. It's a little bit too much. Okay. But the rollers are only an X and 1.
Yeah, they don't have a regular.
I think it's an example from the notes.
Yeah.
Yeah, they don't have like an X, Y roller.
Yeah, they pretty much. I mean,
Honestly, most of the time they have a truss on a roller, and it's not like that. You're going to have a situation where in class where you have it's just not a statement. So the reason most of the examples of the book are like that is because that's the only statement. So if you look at that example, the roller 145, it looks like this, then it will be statement.
Right.
So rollers are usually really difficult to do for truss pump because you have to angle it perfect.
Right.
Otherwise, it's just.
so I mean, you see that.
Also,
Take it out. This is a good one.
yeah.
When you have a spring that's at an angle, you basically just do K times that.
Correct. Yeah. And so instead of E over L, you just have K. Yeah. I mean,
I did it, and I mean, I got
pretty nasty.
the values wrong, but I had like what was supposed to be 0, 0 in Matlab, and I'm like, yeah. I wrote that in my code. I'm like, I'm good with this.
Yeah, don't stress about that frame much. I mean, give it a try at least, but don't if you don't get the solution. I would focus on it. The frame stuff, I have that there just so we can test our code. Once you have the code written, we repent on the frame. So that's all.
I've literally got this done for like over a week. And I'm just like I've been procrastinating because I finished this right after you finished talking about this stuff.
Yeah.
And then when you did the frame example, I was like, I just saw that and I was like, I really don't want to do that. Yeah. Like, because I did that after you finished it like right away, and then as soon as you finished frames, I was like, no way am I gonna do that.
Just try it once, and then, you know, if you don't get it, don't worry
All right, I'll just put some down on paper.
about it.
Can I give this to you though? And then turn in my MATLAB and the other one online?
Sure.